Welcome back to our lecture series in engineering mechanics. And as I promised to you in our last lecture, we will now expand our knowledge to look at the equilibrium of particles in a 3D coordinate system so that we can actually analyze systems as they exist in the real world. For some reason, students sometimes initially are a little bit afraid about 3D systems, especially when it comes to calculations in 3D. But my goal today, of course, is to show you that all we have to do is expand our already existing knowledge from the 2D world so that we can move into the 3D world. And the reason we are doing that is so that we can calculate the forces in 3D cable structures. That is our first step into 3D systems, so that we can talk about that on a general level. And to ease us into the topic, I also want to use this as a chance to talk about symmetry or structures with symmetry, to show you that there are some conditions that you can take advantage of when you solve these problems. And ultimately, of course, our absolute goal in this lecture is to really calculate randomly oriented cables in 3D structures so that we can be prepared and solve any scenario that will be thrown at us. So without any further ado, let's get started and talk about the equilibrium conditions in 3D. And the best place to start, as I mentioned before, is by where we left off. So let's go ahead and start with a two-dimensional coordinate system. And usually we have a two-dimensional coordinate system which looks like this, x and y. And what we've learned so far is that all we have to do is say that we have the sum of the forces in x being equal to 0. And then we start our actual equation. And we also state that x is positive to the right. And we did the same for the y-axis. So the sum of the forces in y is equal to 0. And we defined that as upwards positive. And now I'm going to draw a coordinate system that I usually don't draw in this class, with the z-axis coming out of the plane. You see that in other classes. In this class we usually don't do that, but my goal is to expand our knowledge. So I'm going to make this the z-axis, the positive z-axis. And so what that means for my equilibrium condition is that now I add another equilibrium condition, which of course reads the sum of the forces in the z direction being equal to 0. And I have to state that it's positive in the diagonal outside of the plane in this case. And what that means now is that we are ending up with one more condition. So we had these two conditions before. We now have a third condition. And I want you to think about this for a second, what that really means. And let me take you back to the 2D condition. What we did when we had 2D systems was we always solved for two equations with two unknowns because we had these two conditions. So this allowed us to solve for two unknowns. And the reason for that is because we had two conditions. But now we are actually adding a third condition. So now we added a third condition. And therefore, we can now solve for three unknowns at a time. So solve for three unknowns at a time. And that, of course, is very important to understand. So let's highlight this, that you can solve for three unknowns because you have three conditions now. Now, what that means is that our math becomes a little bit more complicated because, of course, we're having three equations now and we need to solve three equations with three unknowns at a time. But what I will show you initially is that often you can take advantage of some aspects of the structure to reduce it to one unknown or two unknowns. Of course, at the end of this lecture, we will be ready to solve all three equations with three unknowns at a time. But again, my goal here is to show you that 3D equilibrium problems are not as scary as you might think they are. So let's move on and let's go to the equilibrium equations in 3D. And to do that, I'm now going to draw the correct coordinate system that I usually use in this class. And that means that I usually have the x-axis coming out of the board and the z-axis is going upwards. So remember our right-hand coordinate rule. So let's say here I have x, and here I have y, and then here I have z. And probably to better orient ourselves in the coordinate system, it's better to also add the negative direction. And then I'm going to place, let's say, two forces in here. Let's use a blue force that goes somewhere into the third octant. Let's say that goes here. And it goes all the way into this direction. And then I also want to add a second force. Let's make that purple. That actually comes out of the board in this case. And so I'm going to make that look like this. I have to parallel move my axes. So that I, of course, have all three components. And let's call this F1, and the other one I'm going to call F2. And you may already notice that this system could never be in equilibrium. So I'm going to add a third force to it, because right now everything is just pulling up. Right? Let's take a look. This is going in the positive z direction. This is going in the positive z direction. So this system could never be in equilibrium. In fact, this should from now on make you clinch. You should say, why is there nothing to balance these two upwards forces? So I'm going to add a downward force right at the center. This could be like, for example, our traffic light that's hanging there. So I'll add a force right here at the coordinate origin. And there's the point that connects them. And let's call that F3, which only has a z component. So now I can go ahead and actually develop my equilibrium conditions and equations. And of course, my conditions for pictures like this, I can always blindly write down as first the sum of the forces in x is equal to 0. And the sum of the forces in y is equal to 0. I can do that without even thinking about it. And the sum of the forces in the z direction is equal to 0, because that has always to be true. Now I need to take a look at the diagram and see in which direction those forces are acting. So x is moving in that direction, Fy is going to the right, and Fz is going up. So now let's develop our equations. So I can say that 0 is equal to, let's start with our F1, which is going in the positive x direction, so plus F1x, and F2 is actually going in the negative direction, so minus F2x, and then there's no F3 acting in that direction because F3 is just in the negative z direction. For the y direction, I have to start with my F1 as well, which again is positive, so plus F1y minus F2y and no F3 component. But in my last equation that looks different, so now I have to state that we're looking at positive F1z and positive F2z, but minus F3. And that is literally everything you have to do, because now you have established proper equations with three unknowns effectively. Well, Actually, sorry, that's not really true. Right now we have up to 9 unknowns here, but you already know the trick that we have to do next. So right now we have f1x, f1y, and f1z, and those are 3. And then we have f2x, f2y, and f2z, and those are another 3. And then you could have the same thing for the third direction, which here we don't do to get the problem across. But you know the trick that we have to do to turn these equations into 3 equations with 3 unknowns. We would have to express these forces now, or these force components, in terms of their parent force, if you want to call it that way. So, for example, you somehow can turn F1 into F1x, right? So I can use this force and project it onto the x direction, for example. And that, of course, is best shown in an example, but please understand that you can express this, this, and this in terms of F1. In fact, let's, for that force, write down that here we have F1x, and here we have F1z, and here we have F1y. And of course, I know that they point in these directions. Otherwise, they could not move from this point to this point. And I say that again so that you develop a good 3D understanding of these problems. So to move from this point to the end of F1, you can either go along F1, or you can, for example, go to the right first, then out of the plane, and then upwards. And that's how you assign the proper directions here. And that is important so that you understand where the plus and the minus is coming from. Of course, I did this without these arrowheads here already, but this will clarify this a little bit more for you. So that means that we can use these equations and conditions in 3D as well. And just for our general understanding, because it's so much fun, this is the 3D equilibrium condition. And then what we see here is the 3D equilibrium equation. And that will always work. Again, of course, you have to express them in terms of 3 unknowns. So that will be our next step. So let's go ahead and write that down. So ultimately express these functions in terms of 3 unknowns. So that means in this case f1x, f1y, and f1z all are expressed through f1. Likewise, f2x, f2y, and f2z are expressed through f2. So these are the important ones. Let's highlight them. So this is what you really have to plug into your equation ultimately. But again, that is best shown in an example. Just for clarification, this down here is the free body diagram in 3D, and I encourage you to always use this to express your equations. And my experience in the classroom is that sometimes students don't want to draw, or sometimes students think that drawing is a waste of time. I would beg to differ a lot on that. The more you draw, the better understanding you develop of the 3D problem, and the more likely or the less likely you are to make a mistake here in your equation. So I always encourage students to draw the free body diagram no matter what, if it's requested or not. But that concludes the introduction to the equilibrium in 3D. And now, believe it or not, we are already ready to move on and solve our first problems.